Hi, how are you going? In this video, what I'd like to go over is a review of Chemistry 2.4, that is Achievement Standard 91164. I'd just like to go over the most important points that you need to know and be comfortable with in order to be successful in the exam for this with this paper. So let's just quickly go over the core concepts that we need to be able to understand in order to be successful. The first thing we need to be able to do here is draw Lewis structures, followed by, once we've drawn the Lewis structures, we want to be able to use those Lewis structures to identify the shapes of the molecule of the Lewis structure, and then write a paragraph justifying the shape of the molecule. Once we've identified the shape of a molecule, we also need to be able to write paragraphs justifying the polarity of the molecule. Is the molecule polar or non-polar? Okay, so once we've done all of those four related topics, we're going to then look at molecular substances, the four different types of molecular substances, and we're going to justify their properties using their particles, their structure, and bonding. Now, the metallic substance is one of them that we're going to identify, and usually when we're talking about metallic substances, we'll justify its malleability, its ability to conduct electricity, and its melting point. And then we're going to look at ionic substances. Ionic substances, again, we're going to look at what is the melting point of ionic substances. Why do ionic substances not conduct electricity even though they have charged particles? And why is it that ionic substances are able to dissolve in polar solvents? When we look at covalent networks, in particular, we're looking at low melting points due to the weak intermolecular bonding. We also maybe, with these ones, are going to talk about their solubility. That is, they're not soluble in polar solvents like water, but are soluble in non-polar solvents like hexane. So we are also, and I missed this out, going to talk about covalent networks. And when we talk about covalent networks, we're talking about silica and graphite or diamonds. So once we've done all of talking about different types of substances, we're going to have to ask some questions about enthalpy changes or energy changes. And we're going to have to be able to recognize whether something is endothermic or exothermic based on observations or data that's given to us. We're also going to have to use data from an equation to sketch a labeled graph of the enthalpy change. Another last couple of things we have to do are a couple of calculations. The first calculation that they might ask us to do is use a given equation with a enthalpy of reaction value and mass or moles given to us to solve problems. And the last type of calculation we might need to do is use bond energy values to calculate estimates of the enthalpy of reaction. So these are the 12 major types of questions I'm going to ask in this exam paper, and I'm just going to go in a bit more detail about each one of these. Right, okay, Lewis structures. Now, Lewis structures are really important, remember, for identifying the shapes of molecules and also being able to work out whether a molecule is polar or not. Now, how do we go about drawing Lewis structures for a given molecule? Well, the first thing we need a periodic table. And the periodic table has, along the top, it has a group number given to it from 1 all the way across to 18. And we use the last number of the group number to tell us how many valence electrons there are. And the first step we do for a molecule is we're going to count the total number of valence electrons. So here on the periodic table, I've written the numbers 1 through to 8 to represent the number of valence electrons that are contributed from the atoms in each one of the colored columns. So if you when you do this exam, you will be given a periodic table, and each column will have a label from 1 to 18. And the key here is just to look at the number that is furthest to the right. So if it's 18, the number is 8. If it's 13, the number is 3. And if it's 2, the number is 2. And we use that to count the total number of valence electrons. Let's have a look at an example. So if we have carbon sulfide, And what we've got here is a carbon atom, which is in group number 4, so it's going to have 4 valence electrons, and we have sulfur atoms in group number 6. So there is 1 carbon atom and 2 sulfur atoms, so that's 4 plus 6 plus 6. That gives us 16 valence electrons to place around the molecule once we've drawn it. Now we're going to draw the carbon in the center because it has the most unpaired valence electrons if we were to draw the Lewis structure just for the atom. And we're going to draw the other atoms adjacent to it, left and right here, and put a bond between them. Now we're going to, for the outside atoms, make sure each outside atom has 8 electrons allocated to it. Now this bond between the sulfur and the carbon actually represents 2 electrons, but it's just drawn as a bond. So we're going to add 6 more electrons around the left-hand sulfur, and we're going to do the same to the right hand. It has 2 here. Let's add 6 more. Now notice what's happened here. I've used all of my 16 electrons that have been allocated to me. I have none left. So now what I'm going to do is I'm going to check that each atom has its allotment of number of electrons it's supposed to have. So the sulfur, yep, it has 2, 4, 6, 8, and the sulfur on the right has 2, 4, 6, 8. However, the carbon in the middle, in this case, so this is my number 5 point here, as we check to see everything has the right number of electrons. It doesn't. It has 2, 4. So it's actually 4 electrons short of 8 it requires. So what we're going to have to do is shift 2 electrons from this sulfur and 2 electrons from the sulfur on the right. We put them around the atom in the middle, and we're left with this molecule here. Now, whenever we have to shift electrons to make sure that the center atom has enough electrons around it, 8 electrons, or 6 if it's just boron, we need to be sure that we're taking the electrons either from something that will make a double bond. So you can't take electrons from a chlorine because it will only make 1 bond. You can't take it from a fluorine. You can from a sulfur or an oxygen or a nitrogen. Okay, that's all we need to talk about Lewis structures for the moment. Okay, let's look at the shapes that can be formed from the Lewis structures you would be expected to draw at this level. So at this level, we've got 3 basic frameworks, or I would call base shapes, for the shapes that could be formed. The first, the simplest shape, I guess, is a linear base shape, and that's when we have a molecule that has 2 electron density regions around the central atom. In this case, we can see that there are 2 double bonds around the carbon dioxide central atom here. Now, because these are electron regions, are regions where electrons are confined to, and they are around the center, these bonds are going to push away from each other as much as possible, and they'll produce this linear shape with 180-degree angles between the bonds, or the electron regions. Now, if we were to look at the next shape, which is what's called a trigonal planar base shape, so the next 2 shapes are based on the trigonal planar framework, or trigonal planar base shape. We have the one shape where we have 1 central atom with 3 regions around it. So in this case, there are 3 electron bonding regions. These regions will push away as far as possible from each other, producing this 120-degree angle. Now, because this shape here, there are 3 bonding regions, but all 3 of them are bonding, it produces an overall shape of trigonal planar. So it's based on a trigonal planar base shape, but overall, in this case, it's trigonal planar. Now, I'll just explain in more depth what we mean here. So this next molecule here, hydrogen nitride, I'm not sure whether that's the right name here. Anyway, so what we've got here is a nitrogen as a central atom, and we've got a double bond, a lone pair, and a single bond around it. Now, these are all regions of electrons, and they're counted as equal when they push against each other. So they produce a trigonal planar base shape, right? So that's the framework. But because there's 3 regions producing a trigonal planar base shape, but only 2 of them are bonding, the actual shape of the molecule represents a bent shape with a 120-degree angle. Okay, so this is these are three different shapes. The first one based on linear shape, and the next two based on trigonal planar base shape. The next three shapes are going to be based on what's called a tetrahedral base shape. Now the first two are a bit easier to remember because their shape is two-dimensional, but a tetrahedral shape is a three-dimensional structure, so we can't represent it as tidily on a sheet of paper. But in this case here, for methane, if we have a carbon in the center and four regions of electrons around it, they will repel away from each other as much as possible, and they will produce this shape here with the dark, so the triangle line here that's shaded in is representing a hydrogen coming out from the screen towards you, and the dotted line is a hydrogen going to the back because it's trying to represent a three-dimensional shape. Now the angles between the electron regions or the bonds here are 109 degrees. Now this is a tetrahedral base shape, the frame, but every single bond, there are four regions, but all four regions are bonding, so the overall its shape will be tetrahedral. Well, what if we had something like ammonia, where we had a base shape, four regions, tetrahedral base shape, but only three of them were bonding? Well, we get this shape here that looks a bit like a triangle pyramid, or trigonal pyramidal, we can call it. It still has 109 degrees between the angles, but there is, you can see that there's no bond going upwards because there is a lone pair of electrons there. So the shape of the molecule would represent a triangle pyramid. Now, what if we had two regions were bonding and we had two non-bonding regions? Now we can look at this and it kind of looks like a linear shape, but we need to remember when we're talking about four regions of electron density around the center, we're not explaining this in two dimensions, it's in three dimensions. So we're looking from above, and what is this actually represents is a bent shape, right? So there are four regions pushing away from each other as much as possible. They make a tetrahedral shape, and because there are four regions, the angle is 109 degrees between them, and the overall molecule of water here is going to be bent. And remember, that's because there are four electron density regions and three are bonding. That means two are bonding and two are non-bonding. Now it's really important that we remember that four electron density regions will always make a tetrahedral base shape, and then remember that the 4, 3, and 2 will make different shapes depending on the number of bonding regions they have. Okay, so now let's say that the next thing that we're going to expect it to do, so let's say we've remembered those 6 shapes and how they come about from Lewis structures. So when we look at this shape, the first thing we can do is go, oh well, look here, there's 4 electron density regions around the central nitrogen atom, so that 3 of them are bonding, so it must have a base shape at tetrahedral, but because 3 are bonding, it must be a trigonal pyramid. Okay, that's fine. But we're going to have to explain in detail in a paragraph why this comes about. It's a question they're going to ask us. And the way that I always remember this is I have an acronym called SARASBO, and it has 7 important details I need to have in the paragraph sort of pop out when I use that. So let's just have a look at this. Before I look at the SARASBO, just remember that a dot on top of the central atom here is a lone pair of electrons, a pair of electrons not involved in bonding. A line is a single bond, and 2 lines is a double bond. They are all regions of electron density. Now let's go back to SARASBO. When I say SARASBO, here it is, SARASBO. Okay. Now, C stands for the central atom. I need to say that there is a central atom. And then I need to say how many electron density regions are surrounding that central atom. Then I want to talk about that these regions will repel for maximum separation and give the angles that they will form. If there are 4 regions, they will form 109 degree angles. If there are 3, 120. If there are 2, 180. Once I've covered all the first SARAS bit, I need to say the base shape. The base shape for this is tetrahedral. That's not its final shape, but it's the framework that it's based on. Then I'm going to talk about how many of these regions around the center are actually involved in bonding, because that will influence the final overall shape, and then give the final overall shape. Let's give it an example, this paragraph. So let's have a look. The central atom, okay, C here, is surrounded by 4 electron density regions. That's the E from Ceresbo. These regions repel for maximum separation, R, to produce 109-degree bond angles. So I've covered the first 4 parts up to this part of my explanation. This produces a tetrahedral base shape. Okay, S, given the base shape. As 3 of the 4 electron regions are bonding, I've talked about the number of bonding regions. In here, if you want to be thorough, you can also say, and 1 is non-bonding. The overall shape, that's O, is trigonal pyramid. So this is me. I use the acronym Ceresbo to make sure I include all of those 7 important details. The central atom, number of electron density regions. I state that they repel for maximum separation. I give their angle, their base shape. I say finally how many of those regions are bonding, and therefore what the overall shape is. Now we're expected to explain any shape that's given to us from a Lewis structure. If we're going to write an excellence question in this paper, I'm going to be expected to compare 2 different Lewis structures. Now I can do that by writing 2 separate paragraphs and then writing a statement at the end that summarizes the similarities and differences. Okay, so we've done that paragraph. They're also going to expect us to write a polarity paragraph. Now polarity paragraph is, okay, I've worked out what the shape is. Is this molecule polar or not? So to remember whether a molecule is polar or not, I use the acronym UBAC. Okay, UBAC is for me to remember the 5 things I need to include in my paragraph. I need to talk about a difference in electronegativity, that these 2 atoms bonded together share their electrons unevenly. Because of that, they produce a bond dipole and therefore a polar bond. Whether they are asymmetrically or symmetrically arranged, that is the bond dipoles, and that these bond dipoles either cancel or don't cancel out to produce either a polar or non-polar molecule. Let's look at it as an example. So here's the molecule at the top here. We can see that it is ammonia and it's a trigonal pyramid. Okay, so N and H here, because they are 2 different atoms, they have a difference in electronegativity. In fact, here, nitrogen is more electronegative than hydrogen, so it gets a slight negative dipole moment, and hydrogen gets a slight positive dipole moment. Because they have a difference in electronegativity, they share their electrons unevenly, producing these dipole moments, which in essence produces what we call a bond dipole. Notice this little green arrow here. It has a wee line on the positive end, and the arrow represents the negative end. So here, this is a bond dipole being produced by an uneven sharing of electrons between 2 different atoms that have a different electronegativity. In fact, any different atoms have a difference in electronegativity, so we can use the same argument anytime. So, yeah, that's just going over what I've just talked about. Okay, let's have a look at the paragraph I might write at the bottom. So I'm going to write UBAC. So the first thing I'm going to talk about is that H and N share a difference in electronegativity, right? Then explain that they share their bonding electrons unevenly. Here I've said electrons, you should write bonding electrons. This produces a bond dipole, right? This thing here is a bond dipole. Now you can say, okay, this makes a bond dipole producing a polar bond, because a bond dipole is really a factor of a polar bond. It's part of a polar bond. But if we just keep using the word bond dipole, our language is going to be a bit more precise. So the 3 NH bond dipoles are arranged asymmetrically. Now in here you might want to say, because this is a trigonal pyramid shape. I didn't put it in here, but depending on the situation, it might say the shape. You'll put the shape in here. So because these 3 bond dipoles are arranged asymmetrically, right, they do not cancel out. So what doesn't cancel out? The bond dipoles. You never say it's the polar bonds that don't cancel out, because it's actually the bond dipoles that don't cancel out. It's those charges. And therefore the molecule is polar. Now a key mistake that students often make here is they say this molecule is asymmetric, therefore the polar bonds don't cancel out. Well, that is kind of true, but it's not precise. When we get into more complex explanations of these types of paragraphs, and that's the ones where we might have different strength polar bonds in the same molecule, it's really important to say that it is these these polar bonds are arranged asymmetrically. Not the molecule is asymmetric, because sometimes the molecule is symmetric. The polar bonds are arranged asymmetrically. And then the last thing you need to make sure you do is say that it is the bond dipoles that don't cancel, or the poles that don't cancel, not the polar bonds. Anyway, this is most probably the hardest explanation question to do in this paper, and if you can master this, you'll be well on your way to getting a great mark. Overall, if I look at it here, I can see that this is polar. By drawing my polar bonds, I can see that the center of the negative is about where the N is, and the center of the positive is between the hydrogens. Right, now let's look at the 4 different types of substances. So we're going to have to identify the type of substances from the formula, and the way that it works is if you have non-metal atoms in your formula, you're going to be a molecular substance unless you're carbon or your silicon dioxide, SiO2. Those two are exceptions. Any other combination of non-metal atoms is going to be a molecular substance. And what we're going to have is we're going to have molecules, and they're going to be held together by weak intermolecular attractions between the molecules. So notice these little dotted weak attractions between them. Actually, the molecules themselves, the I2, the attraction between the two iodine atoms in the I2 molecule is really strong because it's a covalent bond. We usually don't talk about that. We talk about the interactions between the molecules. So low melting points. So they have low melting points because only a small amount of energy is needed to break the weak intermolecular attractions. Okay, now when we're talking about melting points, it's always specific. It's always the energy that you need to mention. So you link the amount of energy to the weakness of the bonds. It has a low melting point because a small amount of energy is needed to break the weak bonds. If you're talking about hardness, whether it's soft or hard, we talk about it being soft because a small force is needed to break the weak attractions holding the molecules together. So in this case, when we talk about softness and hardness, it's force we talk about. Now, molecular solids, they don't dissolve in water, but they do dissolve in non-polar solvents. Anyway, let's have a look at the non-polar solvents part here, what I'm talking about. So here at the top, I've got some iodine. You can see the weak attractions between them, and some hexane. They have weak attractions between them. Because they both have weak attractions between them, right? When they make new attractions between the iodine molecules and the hexane molecules, those new attractions are just as strong as the weak attractions that they already had, or just as strong or stronger. So iodine is a molecular solid made up of iodine molecules. Cool. So every time we're going to explain the properties, we're going to just say what the substance, the types of bonds and particles that the substance is made up of, held together by weak intermolecular attractions. The non-polar solvent hexane is molecular, so it also has weak attractions. When iodine is placed in hexane, the weak attractions it's formed are just as strong as the iodine-iodine and hexane to hexane attractions, hence it dissolves. But what if we put it in water? Okay, now have a look at this. So these yellow ones here are our iodine molecules with weak attraction. The water particles have strong attractions to each other. Now, even though the iodine molecules would easily break apart, the water molecules have such strong attractions, they are not going to let the iodine molecules move within them. Okay, so and these iodine molecules can't make strong attractions to the water, so they can't displace the attractions they already have. So molecular solids do not dissolve in water because the attractions between the molecules and the water particles are not as strong as the water-to-water attractions. Now, these last explanations, the explanations about the solubility, the dissolving in non-polar, such as hexane, or dissolving in polar, dissolving in non-polar, such as hexane, or not dissolving in water, is going to be one of the more difficult explanations you're going to have to do for this paper. So you have to practice writing these, okay, because they are going to ask you a solubility question. They have for the last 4 years. It's a really high probability they'll ask you. They'll ask you about the solubility of molecular solids, or probably the solubility of ionic solids, and maybe both. Okay, covalent network substances. So there's just really 2 examples of these that they're going to talk about in this paper. Well, there's 3 examples. There's carbon and there's silicon dioxide, but carbon can either be talking about carbon in the form of diamond or carbon in the form of graphite or graphene. Now, carbon in the form of diamond, we have carbon atoms held together by strong covalent bonds. Each carbon atom has 4 strong covalent bonds to other carbon atoms, and they're arranged in a 3-dimensional lattice. And that goes on for millions and millions of molecules in any direction. So actually, in essence, this diamond we see on the left is actually technically just 1 molecule, right? So a substance of diamond is 1 macromolecule, could be called, which is 1 very large molecule, because it has strong covalent bonds between it. Not strong, but very strong covalent bonds. Now, it has a high melting point because, remember, we have to talk about energy. A large amount of energy is needed to break the very strong covalent bonds holding the carbon atoms together. It is hard. Also, that's why you use diamonds to cut very hard substances, because a large force, because we're talking about hardness or softness, we talk about force, is needed to break the strong covalent bonds holding the carbon atoms together. Does it conduct electricity? Well, no, 2 reasons. First one, to conduct electricity, you need free charged particles. You need charged particles, and they need to be free to move. There are no charged particles here. There's only atoms. Atoms are neutrally charged. They don't have a positive or negative charge. So they can't transfer charge, or, to transfer electricity, because they can't move. They also can't because they don't have a charge. Now, this is the same for all covalent networks, silicon dioxide as well, apart from graphite, that is an exception, and we'll look at that specifically. So silicon dioxide here, covalent network made up of silicon and oxygen atoms bonded together at very strong covalent bonds. Each silicon atom is bonded to 4 oxygen atoms in a tetrahedral arrangement. Actually, that's the same for diamond. So, does this dissolve in water? No, the attractions of these atoms to polar water molecules are weaker than the attractions that the silicon and oxygen has to itself. So therefore, it's insoluble in water. Let's have a look at this picture on the right. That's a picture of some graphite. Okay, and let's see if we can explain about the graphite here. Sorry, Okay, so here is a diagram of graphite. Now, graphite's in not a 3-dimensional lattice, it's a 2-dimensional lattice. Now, because each graphite carbon is bonded to 3 other carbon atoms, and if you know that carbon has 4 valence electrons for a start, and then if it only shares 3 of those valence electrons, it ends up with 3 bonds and 1 extra electron. Now, that extra electron is a delocalized electron and acts the same way as it would in a metal. So it can move across the molecule, right? So what we can do is, if we have a charge on one side, a positive charge on one side and negative on the other, these delocalized electrons can move from the over towards the positive end of this charge. So it can conduct electricity. Now, graphite, 2-dimensional network, can conduct electricity because it consists of layers of carbon atoms. Now, what's important here, if you have to explain this one, is they do have strong covalent bonds, but it's bonded to 3 other atoms, and it leaves 1 extra delocalized electron, and this is a free charge particle, so it can conduct electricity. Another thing they might ask you about this, and this is often as an extra question to sort of just separate those top excellence students, is that, okay, we know that graphite is two-dimensional layers, but do you remember that each of those two-dimensional layers is like a layer of paper and a stack of paper, in that the bonds between the particles are really strong. That is, you pull the paper and it's quite strong, but the layers between it's easy to pull one piece of paper off the other because the attractions between the layers are weak intermolecular attractions. So within the layers there are strong covalent bonds, but between the layers they're weak intermolecular attractions. So graphite, two-dimensional covalent network, consists of layers of carbon atoms bonded in hexagonal. That's this sort of honeybee hexagon structure here. I mean honeycomb, not honeybee. They have weak intermolecular bonds between the layers. So if you were to have some graphite on the end of your pencil, a layer of graphite could easily come off the end of your pencil because it is weakly attracted to the next layer above it. Okay, what about metallic substances? Metallic substances are made up of atoms and delocalized electrons. Sometimes you might call them cations and delocalized electrons, because if there's electrons, then what's left is a cation. But I always just use atoms and delocalized electrons. And when I talk about the bonds, I talk about the bonds are between the nuclei of the atoms and the delocalized electrons. And these bonds, I always write them down as non-directional metallic bonds and strong. So I've got that strong non-directional metallic bonds. So metallic solids, high melting point, because you need a lot of energy to break the strong metallic bonds between the atom's nucleus and the delocalized electrons, or the atom's nuclei, that's the plural for nucleus, and the delocalized electrons. Okay, that's fine. Now, that'll be the same reason they're hard as well, right? Because we need a large force to break the strong metallic bonds between the nuclei and the delocalized electrons. Okay, so what about this specific property, that is the malleability? Well, copper is malleable, you can see, and it's because of these bonds again. So I could give the same explanation, but I really need to emphasize that it's because these bonds are non-directional. Now, what does that mean? It means that if these atoms are moved past each other, the old bonds they had will diminish or get weaker, but they will form new bonds next to the electrons that they move close to. So as they move past each other, they will form new bonds without disrupting the old ones, or they can replace the bonds that they are losing. Okay, so why do they conduct electricity? This one's usually pretty straightforward. Metallic solid made up of atoms in a 3D lattice, held together, non-directional metallic bonds. Remember, between the attractions are between the atom, nuclei, and delocalized electrons. So essentially, there are atoms and delocalized electrons. Because these atoms are delocalized, right, that means that they are free moving. Because, so not the atoms, the electrons are delocalized. Because they're free electrons, they are charged. They have a negative charge, so they can conduct electricity. Okay, let's have a look at ionic substances. So ionic substances are basically a 3D lattice of alternating positive and negative charges. Now, that's true for ionic solids that have a 1-to-1 ratio, 1-to-2 ratio. It's a bit more complicated how they're arranged, but we don't need to go into that detail. So we're going to have negative and positive ions that are cations and anions and cations, and strong ionic bonds between them. Remember, strong ionic bonds are just strong electrostatic attractions. They have high melting points because we need, again, a large amount of energy to break the strong ionic bonds between them. What do they conduct electricity when molten? Yes, they do. Why? Okay, so when this is solid, it will not conduct electricity, even though this substance is made up of charged particles. The charged particles are held firmly in place by the strong ionic bonds. They can't move, won't conduct electricity. However, if they're molten, if those bonds are broken and it's in the liquid form, the ions can move and they will conduct electricity because they are free to move. Okay, dissolving in water. This picture that you see here is quite an important picture. In the last couple of years, they've expected you to be able to draw a diagram to show how it is that ions dissolve in water, which means you need to show how the oxygen of a water molecule will be attracted to the positive cation, and the hydrogen side of a water molecule would be attracted to the negative anion. So why do they dissolve in water? Because the water particles, the polar nature of them, means that their negative pole will be attracted to the positive ions, and those attractions are as strong as the positive ions had to the negative ions. Hence, it will dissolve. And obviously, the opposite is true. Okay, why is it that these substances are brittle? Well, if I was to hit a substance with a mallet with a large force, I would disrupt the lattice, and what would happen is as a layer of the lattice moves, the positive ions come in contact with positive ions, the negative ions with negative ions. They then would repel each other and push away from each other to cause a fracture, because the same changes have become adjacent to each other. They're not able to easily just break and form new bonds like metals because they don't have those movable delocalized electrons or those non-directional attractions. Their attractions are very directional, and they're to the adjacent ions above and to the side of them. Okay, so if we were to summarize all this, we could talk about the properties of them. So the first thing, we could talk about the elements. Okay, when we're trying to identify from formula, molecular made up of non-metals, right? So if you see a formula of non-metal atoms, it's going to be molecular, except if it's silicon dioxide or carbon. If we see a formula that has metal and non-metal atoms in it, it's going to be ionic. And if we see a formula with just metallic atoms, it's metallic. Now the particles, if you want to explain the particles, really simple. Molecular has molecules. Ionic has ions. Metallic, atoms, delocalized electrons. Covalent network, atoms. Really, really important to memorize these elements and particles. That is going to be a question in your paper. They usually give a merit mark for it done completely correctly. Okay, the bonds, molecular, weak intermolecular attractions. Remember, they're weak and they're intermolecular. Ionic, ionic bonds. Metallic, metallic bonds. Covalent network, covalent bonds. So really, we're just looking at their name once you've identified what it is, and ionic bonds. We don't have to give the descriptor in it if we were just explaining in a table, but we do have to describe them when we're writing a paragraph explanation. We would expect molecular solids have a melting point lower than 300 degrees Celsius. Ionic solids have a higher melting point, say between 300 to 1200 degrees Celsius, and metallic also are higher. Some metallic, like mercury, have a really low melting point, but generally they have higher melting points. Covalent networks have very high melting points. Again, the properties, molecular should be soft, ionic because they're stronger bonds, hard like metallic. Then covalent networks are very hard because they have very strong bonds. Conductivity, molecular, no. They don't conduct electricity very well because they don't have a charge, even if they can move. What about ionic? Well, they won't conduct when they're solid, even though they have a charge. They're held firmly in place. When they're molten or dissolved, those ions can move, therefore the charged particles can conduct electricity. Metals always conduct electricity because there's always those delocalized electrons. Covalent networks, no, don't conduct electricity, except if you're talking about graphite, those two layer, because it has two-dimensional layers and it has three bonds between the atoms. The carbon atoms has one electron left that's delocalized, and it can conduct electricity. Okay, when they talk about brittle and malleable, they're usually only talking about ionic and metallic because those are easy to explain. Soluble, they're mostly talking about molecular are soluble in non-polar solvents, and ionic are soluble in polar solvents. Metallic and covalent, not soluble in anything really. Okay, so the last ideas that we need to go over for this paper is enthalpy. What is enthalpy? So remember, enthalpy is heat energy. The heat energy specifically that's evolved, given out, or taken in from a chemical reaction. So we can have exothermic chemical reactions. That's when we are forming bonds. The temperature is increased. We notice that something's getting hot. We know that chemical potential energy is turning into heat. We can see a delta RH that is a negative value, or we can see heat given off. Now, temperature increase will be if we put a thermometer and we measure the temperature increase. Now, here's an example of an exothermic reaction. It's an exothermic reaction because the delta RH for this, or the change in the reaction enthalpy, is negative. It's negative 94. Often what they'll ask you to do, they'll give you this and you'll have to explain why this is exothermic. Pretty simple. Delta RH is a negative value, so it's exothermic. The second thing they'll ask you to do is label an energy diagram. And they'll give you maybe an energy diagram or ask you to draw one. So what we need to know is that on the left are the reactants and on the right are the products. And in this case, we have to write down what the reactants are. So here, I'm going to put nitrogen plus 3 hydrogens. And then I'm going to put the products. Here, there's 2 ammonias, right? And I'm including all the details that's from the equation here. Then to label this diagram properly, I can now show what delta RH, what it represents. It represents the difference in energy between the products and the reactants. So I'm going to draw the arrow here in a dotted line that is horizontal to this top line, and I'm going to label that as delta RH and give its specific value and unit. So that is a perfect label diagram. They might expect us to do the same for an endothermic one. We need to remember endothermic is bond breaking, temperature increase, heat is the heat energy is being absorbed and turned into chemical potential energy. Delta RH is positive. So here's an example of an equation. Notice delta RH here has a positive value in front of it. So we're going to draw a energy diagram that is starting with the particles having a lower amount of chemical potential energy, and in the end they're going to have a lot. And that chemical potential energy came from the heat that was absorbed from the surroundings. So I've written the reactants on the left and the products on the right, and here again I've drawn a dotted line, an arrow to show delta RH. Here it equals positive because the particles have increased their energy. On the left, remember, the particles lost the energy. Their energy is given out as heat. The particles increased it because they sucked in the heat energy from the surroundings. That's why it felt cold. Okay, finally, we've got a couple of calculations we need to do to finish off this paper. So the type of calculations we're going to do is we need to be able to use the moles equals mass of a mole mass formula given to us in the resource paper. And we need to do a calculation involving Q, which is energy equals the enthalpy of reaction over the coefficient times the moles. This formula on the right is not given to you. If you can remember a formula instead of just intuitively answering this question, it might be more beneficial for you. So let's look at an example of a question. Ethanol, C2H5OH, can be used as a fuel. The equation for the complete combustion ethanol is given below. There it is. We can see that this is an exothermic reaction. It's giving off heat. Now, what they want us to do for this question is calculate the energy released when 5.3 grams of ethanol reacts. Now, notice this equation is telling us what energy is released when 1 mole of ethanol, because there's no other coefficient in front of here, so that means 1 ethanol would produce exactly that much energy. So what we want to work out for a start is how many moles of ethanol is actually 5.3 grams. Then we can find out the amount of energy that it would release. So the moles of ethanol equals the mass divided by the molar mass. Now, if you're not sure what it is you're actually calculating the moles of, it's really easy. They're always going to give you the value for molar mass. So you look and you see, oh, big M here, it's ethanol, so I'm going to use the grams of ethanol. Cool. So I did that. I worked out the answer is 0.115 moles. Fantastic. Now, the question asked us, though, how much energy. I want to find Q here, so we're going to use this equation. Q equals delta RH divided by the coefficient. Now, what does the coefficient mean? It means the big number in front of the substance I'm talking about. Remember, I go back and look, I'm talking about ethanol because it's the one I'm given the molar mass. I go to my equation. The coefficient in front of here is a 1 because there's no number. So Q equals delta RH, which is minus 102, over coefficient of 1 times the moles. I solve this, I write the answer to 3 significant figures, and I put the unit down. It's that many kilojoules. Minus 11.8 kilojoules. How much energy is released? Well, you could then write an answer and say, well, that's 11.8 kilojoules released. Of course, that's what the sign is saying. It's exothermic, so it's 11.8 kilojoules released. Okay, so they might ask you this way, but they might ask you the following question. So here's another one. Ethine is a common fuel used in the welding industry. The equation complete combustion of ethine is given below. There it is. Okay. Now, calculate the mass needed to give that much energy. So they've actually put in it around a different way. So I want to find out the mass. So in order to find the mass, and they've given us the molar mass, I need to know the moles. To find the moles, I need to calculate the rest of this equation. And I'm going to have to rearrange this equation. So I'm going to use the Q equals delta RH over coefficient times N. But this fraction of delta RH over coefficient, I need to move to the other side. And when I move a fraction to the opposite side of an equation, what I essentially do is I just flip that equation upside down when I rearrange it. So here, actually, I haven't even done that yet. I've just substituted it. So let's substitute the values in. Because if we substitute them in, for a start, and my algebra isn't that good, they're actually going to give us some grades for putting these values in here, going to give us an achieve. So I'm going to put these values in here, and then I'm going to solve. Now, the way that I solved this is I took this fraction and flipped it to the other side and multiplied it by this, and I got this answer. Another way you can do it is you can put it into your scientific calculator, solve for x, n is your x. Either way is fine. So I got that many moles. I'm then going to use the moles equals the mass over molar mass. Here's our molar mass. I've worked out our moles. Chuck that in. And rearrange, solve, and I get mass equals 120 grams. So those are the two types of questions we might get for enthalpy calculations. You have to practice quite a few of these until you're confident with them. Right, so the last type of question we have to do in this paper is how to use bond energy to solve calculations. So the type of they're going to give you some average values of bond energy. So whatever answer you work out to these calculations is going to be an estimation, because a CH bond on average, right? So if I break a CH bond, on average it's going to take 413 kilojoules per mole. But it's going to be a wee bit different depending on the molecule it came from. Did it come from a methane molecule or did it come from a glucose molecule? They're going to be similar, but they're going to be slightly different. So when we're doing it, it's just an average of all of those. So our answer will always be an approximation. Anyway, so what we're going to do is we can find the enthalpy for a reaction, delta RH, by adding up all the bonds broken and subtracting all the bonds formed. In order to do that, they're going to give us an equation that has the actual molecules drawn out so we can see the bonds. They often won't draw it like this, which is I've drawn two O2 molecules. They'll just go put a coefficient 2 in front of one of the O2 molecules, but that's fine. We can visualize this here, and in this case we can see that there are 4 H to C bonds that are going to be broken. There are 2 O double bond O bonds that are going to be broken. There are 4 H to O bonds that are going to be formed, and there are 2 C to double bond O bonds that are going to be formed. So if we put this into a nice tidy rows, so columns in a table, I can calculate that 4 CH bonds gives me 1652 joules of energy, and 2 oxygen double bond oxygen bonds are 996. I can then add all of that up and work out how much energy it would take to break all of the bonds, and I can do the same on the other side to work out how many energy to form all of the bonds. Remember, I'm using this green equation at the top. The energy, or the enthalpy for the reaction, equals the sum of all the broken bonds minus the sum of all the bonds formed. So that's 2,648 divided by 3,358, and I get 710 kilojoules per mole. And that's how we solve it. And this is, so if you are particular and careful about this, this is quite a straightforward question. At the moment, in the last couple of years, however, they've mostly put the question, made it a bit harder, in that they want you to work out the unknown energy of a bond instead of working out the energy of the reaction. So they're still going to give you this equation, but they might say calculate the bond energy. So in this case, calculate the bond energy for the chlorine to chlorine bond. They'll give you an equation, just like we did on the other side, but then they'll give you the answer to the overall energy of the, or the enthalpy of the reaction. So here it's given here, but they want you to find out one of the bonds. So they're not going to give you the value for one of the bonds. You have to find it out. So in order to form this molecule on the right from the molecule on the left, I have to break the CH bond, but I don't have to break all 4 of them because I already keep 3 here intact. So I'm breaking a CH bond, I'm breaking a Cl to Cl bond, I'm forming a C to Cl bond and an H to Cl bond. So I put those into here. Apart from the Cl to Cl bond, I don't have a value for it because they want us to find it out. So it's given the notation here of X. So we're going to solve for X. So, but I'm just going to add it up like I would anything else. So I've got 413 plus X equals 755. I substitute that into this. I get the delta RH from the value given next to the equation. That's minus 102. I substitute in the bonds broken, which is 413 plus X, and I substitute in the bonds formed, which is minus 755. Now I'm going to group like terms and put X to one side by itself. So I need to keep X on one side by itself. Then I'm going to move all of these numbers to the left hand side. So if you can imagine, if I was to take the 413 and move it to the other side of the equation, it becomes minus 413. If I add the 755 to the other side, it becomes positive 755. So essentially what I get is 413 minus 413 minus 102, which is minus 515, and once I move that over there, it was positive 755, and X equals 240 kilojoules per mole. Again, once you've worked out the form of this equation, you can put it into an equation solver, or you can use your algebra to solve it. No matter which way you do it, best of luck. So that's all the stuff that's covered in 2.4, and if you've got your head around all of this and you've practiced doing it, you're going to be really successful, and I wish you the best. Good luck.